real lines which you can see here. So what will happen is that this demand curve has been converted into something which is in the same format in which we have got our capacity curve, which was in the form of your force versus displacement. So acceleration is nothing but mass times acceleration is your force ultimately. So on the vertical axis you have got your force, and on the horizontal axis you have got your displacement, and that is why now what we can do is that we can superimpose your this capacity curve onto the demand curve, and then we can find out where they are meeting. Now what are the various earthquake hazard levels which we have is that we have got various ways in which what we mean by minor earthquake. We have talked about what is the return period. Okay, and Professor Sanvi told us that in our case we have got a return period of about 13 years or something like that. But he was talking about any type of an earthquake which we are talking about. So anyway, there are certain guidelines which are given by FEMA 273, and it categorizes our return periods based on our design earthquakes, based on your minor earthquakes, moderate earthquakes, design basis earthquake, which we call as your DBE, and the maximum considered earthquake, something like this. And these are the various return periods, and further these are the points which we can say are the points of observation. IO is standing for immediate occupancy, LS for life safety. You can say that CP is for collapse prevention. So under the severe earthquake, collapse should be prevented. Under your moderate earthquakes, your life safety should be there, and so on and so forth. So these are the some guidelines which are there, and further we have got certain building performance levels which are defined. As you can say, O is the operational level. For very minor earthquakes, your building should remain in the operational state. So you are expecting very light damage, no permanent drift. There is substantially the original strength. It is almost as if the building is in the elastic stage only. That is what we mean by the operational stage. And negligible damage to powers and other utilities. Likewise, immediate occupancy stage with light damages and so on and so forth. These are some of the things which are life safety is having the structure with moderate damage and so on. And the collapse prevention stage is what we have. These are very clearly defined guidelines which we now from this we have to select in what range of performance we want our building to be. Okay, and depending on that, we can have our standard performance levels which are said as that operational, immediate occupancy, life safety and collapse prevention. You have got your performance levels defined on your capacity curve. I have just explained to you what is the capacity curve. So on this capacity curve, under the event of an earthquake, if it has reached up to this level, you say that it is in the operational level. If it has gone slightly beyond the elastic limit and it has entered the nonlinear stage, then it will be in the immediate occupancy stage. Then beyond that, if it is being pushed, then your building is likely to. So if you have got a moderate earthquake, you will have what you call as your life safety stage, and then the final stage is your collapse prevention. If your earthquake is having a force beyond that, collapse is going to be imminent. Okay, so we cannot change that. So if you consider your pushover analysis as a tool, what we do in the pushover analysis is that initially this is your demand, this is your demand, this is your capacity. The yellow one which you see is the capacity curve, and the reduced demand is because of a few let us say your pushes on either side. So when your building is subjected to backward and forward motion, at that time there will be some plastic hinges which are developing, increasing the capacity of the building to absorb the energy, increasing the damping, and that is why reducing the demand. So this is the final demand which will occur. You can see that this is your final demand curve, this is your final demand curve, and this is where your demand is meeting the capacity. That is what we call as your performance point. So at that performance point, what is the state of the building you can definitely see. So what happens is that when you are constructing your capacity curve, you can construct your capacity curve as long as the building is not collapsing. So you can go beyond this point also. But when you superimpose the demand, that is what is the demand from the earthquake, is what when you superimpose onto that, you come to know that this is the point up to which you need to push your building. Okay, you need not push it beyond this particular point which we call as your performance point. So what is the analysis procedure is that you start with that, you first of all build up the capacity curve, and then you superimpose onto that the demand curve, and then you perform, you will find out what is the performance. That means the hinges, we are going to create some plastic hinges which are there, and that we will be seeing the state of those hinges. So this is what we call as your performance based design. So what are the steps in case of your pushover analysis are that first of all we will select the hazard level, that in what state you want your building to be. Whether you want it to be in immediate occupancy state, whether you want it up to life safety, or whether you want to go up to your collapse prevention. So see, what happens is that our code doesn't specify that to what level of damage your structure will be subjected to. But here you can be selective in that. So what happens is that if your building's capacity versus demand curve, if you have a very heavy earthquake, your demand will be somewhere here, and that is, this is what you call as the performance point. If you got a moderate earthquake, this is the type of damages which you are expecting, and in case of a very moderate event, you will have your structure which is almost unharmed. Now this is what you call as your performance of a ductile structure. In the case of a ductile structure, after this elastic curve, you have got a very wide range of your non-linearity, and beyond that, if a mechanism develops, what will happen is that there will be a sudden drop in the strength of the building, and that is why your lateral shear will be less. And now as against this, if you have got a non-ductile structure, the curve will be looking something like this, where we are reducing. If you see from here, you have got a lot of gap between immediate occupancy, life safety and collapse prevention stages which you have on this curve, and that is grossly reduced. You can see that you have to play only around in this region only, and this is why your non-ductile structures are not preferred. Again, if you talk about the behavior of the structure under earthquake, what happens is that if you talk about the hysteresis loops, which will be actually speaking, what we are doing in the pushover analysis is we are applying only in one direction, but actually speaking, your earthquake forces, when you are giving, it will be moving along like this. Okay, so in the first cycle, it will have a more force as compared to less deformation. Then it will move something like this, go in the other cycle, and it will keep on moving like this. These are how the loops will come, and that is why if I draw what I call as connecting all the points which are there on this side on only one side, that is on the tension side or maybe on the compression side, then what we call is that as a backbone curve. So a backbone curve is basically idealized as something like this. You can see that this is the backbone curve, and on that backbone curve we are going to change it into number of points which you call as A, B, C, D and E. Okay, so if you have different types of structures, like if you have got your semi-ductile and if you have got a brittle structure, you can see where these points A, B, C, D goes. Okay, so in the pushover procedure, what we do is that we have defined certain, let us say, hinges. Even before we apply this load, we are going to have hinges which are defined in the columns as well as in the beams at the two ends, where the maximum stresses are likely to occur, and those stresses are continuously monitored, and finally in what state is that hinge going to occur will tell you. This is what you call as your force deformation criteria. I will not explain further to that. So what we do in the pushover procedure is that we have our capacity curve, then the second one is your demand curve. When we superimpose both of them, we find out what is the state in which your building is, and then decide what we want. So actually, if I speak or if I explain to you what happens in case of your structures, this is a simple model, a 3D model of a simple plane, space frame which has been shown. And if I give a push in the x direction, this is the x direction push, and this is the y direction push, which is also sometimes known as your mode 2. Mode 1 and mode 2 usually are your modes of vibration under for this particular structure. So in case your pushover cases will be defined something like this, that the first push will be given in the gravity direction because your dead loads and live loads are always there. So first all the hinges will be stressed because of the dead loads and live loads. That stress is always there, and then you start pushing the building in the horizontal direction, starting from the end of the stresses which are developed because of your gravity load. So the push 2 and push 3 are the two lateral pushes in the x and y directions. We are considering the gravity loads which are already there. Okay, so your push 1 will be with the full intensity of the gravity load, and once the push 1 is over, the push 1 is we are going to push the building up to the full intensity of your dead load and live load, and then we apply the horizontal pushes in the two lateral directions. We give some target displacement, and the target displacement will be defined as your drift limit. So whatever is the drift limit, anyhow we have to follow that codal provision, and that is why your drift or the lateral push will never be going beyond the drift limit. So the final deformed shape under push one, if I say, this is what will be under the gravity load. So you can see that all the members are deformed because of the gravity load, and then when I give the push in the lateral direction, you will see that the hinges with different colors. Here the hinge color which is up to your elastic limit, then this is up to your immediate occupancy stage is a blue hinge, then your cyan hinge is your life safety, and green is collapse prevention, and so on and so forth. So you can see that there are some 3 magenta hinges which are developing in the first push. We are giving a lateral push. Then in the step 2, more number of hinges are developing. Further in the third step, fourth step, fifth step, sixth step, you can see some of the blue hinges also which are developing. And finally, you can see dark blue hinges and light blue hinges also. And finally, you will see that this is what is going to happen. So as you go on pushing the structure up to step 7, this is how you will be plotting your capacity curve under this push. And finally, you will have your superimposed diagram of your, see, this is your 5% damp spectrum. This is the demand curve with 5%. So initially we had started with 5%. As the hinges start developing, more and more hinges start developing, your damping will go on. See, these are your 5, 10, 15 and 20% damping. These are the curves. Okay, so what will happen is that this is a single demand curve with variable damping, and this yellow line is what you call as your demand curve, which is the red ones are now converted to the yellow one, and then where the yellow one meets the green, which is your capacity curve, this is the point which we call as the performance point. At that point, see, what happens is that when you keep on pushing, your hinges can go up to any, even to blue color, or it can go even to green color. But that is not mattering. What is mattering is that at the time when your performance is met, at that time what is the state of the hinges. If it is in the immediate occupancy stage, you can say that the building is not going to get damaged. Okay, so this is what happens. So in the push 3, some similar graphs are drawn in the two lateral things, and what we mean by hinges in the columns, you can see very well that these are what you have as your hinges in the columns. So what happens is that in your pushover analysis, what we do is that I have given one example, pushover analysis example now we are going to take. It is a ground truss 15-story structure which we had taken up for study purposes without any, let us say, without any shear walls. There were 2 models which were tested, one with shear walls, another without shear walls. And in one model, what we did was that we used only rectangular columns, and in the other model we used equivalent square columns. That is the square columns which are using the same material as the rectangular, but we wanted to compare the performance of your rectangular column versus square columns in this case. And the building data was taken something like this with panel size of 4.5 by 4.5 meters, story height and so on. These are some examples which are given, some loading, how we use the loading, and earthquake loads were given as per the zone number 3 and so on and so forth, the characteristic strength and the geometry which was considered. This is the rectangular column geometry, and as against that we had the building plan with a square column geometry, and this was given to your plastic hinges which were defined were the default plastic hinges were used as the action hinges, the flexural hinges corresponding to your bending moments, and then your shear hinges at the 2 ends of the beam. So beam elements were given flexural hinges at the 2 ends of the midspan, at the 2 ends and midspan. Usually midspan hinges will not be stressed, but still, just because for our purposes, if you have very heavy loads, in case of very heavy buildings, you may have sometimes your midspan hinges also developing, and the shear hinges at the 2 ends. And in the column elements, we had only defined your PMM hinges, that is your axial and the biaxial bending hinges type of hinge. So P, M2, M3. M stands for M2 and M3 hinges at the 2 ends. And then the seismic performance of the RC frame without shear wall. This is a 3D model which was taken up. and then the performance point, if we see, if we compare for the rectangular column, this is the performance point, and for the square column, this is where the performance point is occurring, and you will have, we compared these results, and if you compare the results, what happened was that when both the buildings were following all the codal provisions, still if you can see that there were hinges of the magnitude of LS to CP. What is LS is life safety to collapse prevention. In that range, you had 224 hinges in the rectangular column model, and in the square column model we had 164 hinges which were lying in the range of life safety to collapse prevention. That means it was quite on the non-linear side. So what happened was that if we see this result, then the deformed shape under your push X, if you see the rectangular column and square column, it seems something like this, and further the frame wise hinge formations, if you see at the performance point, this is the figure which shows for various frames in 2D. These are 2D frames which we have